Are you guys ready? Excellent. Okay, so last we left off, there's a couple things that we have to talk about. So in your lab, we'll be talking about the exam. So I think everybody is all kind of caught up in the exam. The exam will actually open up today after your class. And then you guys will have until Friday night at 11:59 to complete the first exam. Okay, but we'll get you guys started. Everybody has their laptops? Good. So we'll get you guys started on some things so you guys will be able to do it without any problems in the future. Okay. So last we left off, I believe we were talking about ionization energy. Is that correct? What is ionization energy? Good. Ionization energy is what? Not so much. So it's along that line. It's a little bit, yes, a little bit you're there. It has to do with those electrons, those dots. So that process is Lewis dot structure, what you're making reference to. Ionization energy. Ionization energy. Yeah.
Is it how much energy you need to get rid of electrons?
So it's how much energy you need to remove an electron. Okay. So now you guys know you're very familiar with the periodic table at this point, right? You're feeling comfortable with it. It's totally understandable. Okay, so on the periodic table, which group is going to have the highest ionization energy? Which group is it going to be really hard to remove a single electron? Okay, thank you. Okay, wait. So you guys say the right side? So tell me, you guys tell me the group. You guys know the group? You'll be able to tell me which group it is. So you're telling me, you're saying it increases from left to right. So basically from group 1 to group 18, it's increasing the ionization energy. Is that correct? You don't know? You got to be confident. You're like, yeah, I know, right? You're correct. That is correct. Okay, so if we look on the periodic table, I have no idea what's going on here. Okay. I hate the screen. Yeah, if you could do that, that would help a little bit. Okay. So here we have the periodic table. So we know that the ionization energy is going to increase from left to right. One way that we know that is kind of logic-wise. We know that group 1 metals. Can you guys give me one metal that's in group 1 metals? In the alkali metals? Lithium, okay? So group 1 metals, those guys, to be stable, they're going to want to do what? Are they going to want to gain an electron? Are they going to want to lose an electron? What was that? Group 1 metals, are they going to want to gain? Are you sure? You want to put money on it? So they want to be like the noble gases, but is it easier for them to gain an electron, or is it easier for them to lose an electron? So if they lose one electron, they're going to be like a noble gas. Which one are you going to do? Are you going to try to gain? Let's see, where's lithium at? Lithium's right here. So you're going to gain 1, 2, 3, 4, 5, 6, 7. So think about it. If you were going to the store, you had a store that's 1 block away from you, and you have a store that's 7 blocks away from you, right? On a day like on Sunday where it was like 110 degrees. Was it how much? 116? 115. Geez. Okay, so 115 degrees, right? Which one are you going to go to? Are you going to go to one block away or 7 blocks away? Does that make sense? So lithium is going to want to lose that 1 electron to be like a noble gas because it's easier for it to do that rather than trying to gain all of those, right? So it wants to lose. So do you think its ionization energy is going to be high or low? That's right. Its ionization is going to be low. It's going to be very little compared to something like fluorine. Fluorine, do you think that's going to want to lose an electron, or do you think it's going to want to gain an electron? It's going to want to gain an electron because then it's right like neon. Okay, so in that case, if you take an electron from it, do you think it's going to be really hard to take it from it? Or do you think it's going to be like, yeah, you know, I'll go ahead and give it? It's going to be hard, right? Because it's one away from being a noble gas. Why in the hell would you give up your electron if you're this close to being a noble gas, right? Make sense? You answer that. We've been talking about it the whole semester. You should be able to help me out with that one. Why would you want to be a noble gas? Because it's stable. It's perfect, right? Don't you want to be perfect? Okay. So if we think about when we have reactions, right? So what's happening in the case of like sodium, right? So sodium is going to want to lose that electron, right? So it's going to drop its electron, and then something like chlorine is going to come along and try to pick up that electron. And so that's how we're able to sit there and get that exchange, right? So sodium loses its electron, chlorine is going to be able to pick up its electron, okay? So ionization energy is just basically the energy that it takes to lose that very first electron. Now, you could have a second ionization energy. That means the energy it takes to lose 2 electrons. You lost the first one, and now you're able to lose the second one, right? And so if you look at the trend, first with the first ionization energy, this is just basically showing you the trend, right? So if you look at helium has the highest ionization energy because it's a noble gas. You're already noble. Do you want to lose or gain anything? You're perfect. I'm perfect. I don't need to do anything. So I'm not going to do anything, right? So that's the concept of the noble gas. They're not going to want to gain anything. They're not going to want to lose anything, right? So their ionization energy is going to be really, really strong, okay? Where if you get down here, lithium, really low compared to the others. And so you guys can kind of see the trend. And as you go across, you'll notice that you have an increase overall. Now you get this little blip here with nitrogen. Nitrogen is kind of a special species, right? It does some weird things, and we'll talk about some of the things that nitrogen will do later on. There's reasons for it, and it's a little more complicated that we won't go into in this class, but if you guys ever take my 1A class, we'll definitely go into it. Chem 1A, general chemistry. Yeah, this is intro. I know it's weird. Yeah, this is intro. I think it's easy. Yeah. Some people will tell you it's easy. Some people say it's hard. It just depends on. Organic is a lot of memorization. It depends on the type of student you are. If you're good at memorizing, it could be real easy for you. If you're not as good at memorizing, it could be really hard for you. There's a lot of memorization, but there's a lot of chemistry, general chemistry in it as well. Okay, back to this. Second ionization energy, again, is the energy that it takes to remove 1 more electron from something that you've already removed an electron from. Okay, so like for instance, Na+, right? Na+, we've already removed that 1 electron from it. So if we have Na+, okay, so Na+ is going to be like what noble gas? It's going to have the same number of electrons as what noble gas? Sodium plus.
Neon?
Neon, that is correct. So it's going to be just like neon in terms of the number of electrons it has. Okay, so it has the same number of electrons as neon. Now, isn't neon, it's noble, isn't it stable? So what do you think the ionization energy is going to be for like neon? Is it going to be low or is it going to be really, really high? It's going to be really, really high. So what do you think the ionization energy is going to be for Na plus? Now that it's already lost that very first electron. Is it going to be really low or is it going to be really high?
High.
It's going to be high because it's going to be just like neon. It's stable now, right? It's happy. It's like, I'm finally happy. You know, it's best being where I'm at. And now you're going to take something from me? No, that's not going to happen. They're going to fight you for it, right? So when you remove that very first electron, depending on where you're at, your ionization energy may go up or it may go down. But let's say, for instance, if we have Mg plus. Where's Mg located at? Group what? Group 1, group 2, group 3, group 4, group 5, group 6?
2.
Group 2. How many electrons does Mg needs to lose to be like the noble gases?
2.
It needs to lose 2 electrons. Now, if I lost 1 electron, so do you think the ionization energy for Mg plus is going to be greater or lower than lower, right? Because it wants to lose that other electron. It's anxious, right? So it's going to have a lower ionization energy. So in that case, this is losing that very first one. Its second ionization energy is going to be really low. It's actually going to be lower than that first ionization. Okay, do you guys understand? You see how that works? Okay, and then there's the third ionization energy. That will be the process of losing 3 electrons. You lost the first one, you lost the second one, and now you're looking at the energy to lose the third one. Okay, so this is the general trend. All right, as we go from bottom to top, the ionization energy increases. As we go from left to right, the ionization energy increases. Make sense? Okay, let's see how good you guys are at this. So we have list each of the following groups of elements in order of increasing first ionization energy. So increasing so do you guys think the order is? Oh, in the order that it is on the screen, B, E, N, and F. So it's like this. Okay, how many of you guys think this is right? Raise your hand. You guys can raise your hand on the screen too, for those who are on the screen. How many of you guys think it's some other order? What do you think it is? You said F, then you said BE, and then you said N. F has the lowest? Okay, so you're telling me fluorine. Fluorine is 1 away from being a noble gas. It's going to be willing to give up an electron from losing 1. Okay, so the correct answer is this up here. That is the correct answer, right? Because ionization energy is the energy it takes to remove that very first electron, the first ionization energy, the very first one. Okay, so fluorine does not want to lose an electron. It wants to gain electrons. So it's going to be like, no, I don't do that. Right? And nitrogen, we look on the periodic table, nitrogen is located, let's see. Right here, right? So fluorine is the closest to being a noble gas. Nitrogen is a little bit further away, and BE is the furthest. So BE is going to be the one that's going to be most likely to lose an electron. It's going to have a lower ionization energy. Okay? Okay. So it's important to make sure that we understand the question that's being asked, right? Because that's how we always end up getting screwed on multiple guess tests. Okay, so I've talked to you guys about chemical groups. So things that are in the same group are going to behave the same way. So we call them chemical families. So like group 1 metals, that is the alkali metal, alkali. Doesn't that sound kind of rough? Alkali, right? I belong to the alkali, right? It sounds pretty, pretty rough, right? So they're known to be very reactive. They're one away from being a noble gas. They want to get rid of that electron. So they're going to be reactive. Okay. Group 2 metals, alkaline metals. Okay. Group 2 metals, those guys aren't going to be as reactive as group 1 metals. Alkaline, doesn't alkaline sound a little softer than alkali? Alkaline, right? Alkaline metals, those guys, they do react. It takes some effort for them to react, right? And then on the other side, we have the halogens. Pull up my periodic table here. So these are the halogens. Group 17. They're one away from being a noble gas. So do you think they're going to be very reactive, or they're going to be like, I don't know. You know you're not stable, right? We know that anything, unless it's a noble gas, isn't going to be stable. You're really close to being stable. You're going to be like, I don't know about that. Exactly. You want to be stable, right? Stable means low energy. It means you can relax. You get people serving you drinks. You want stability, right? You're not going to want to sit there and hang out with crackheads and, or anything like that, right? So you want that stability. You want that good life, right? Okay. So in that case, you're going to do pretty much anything to get that one electron, right? And so you're going to be very reactive. So the further you are away from being a noble gas, the less reactive you typically are. Okay. So for instance, if we compare fluorine to oxygen, so oxygen belongs to the halogens, right? That's that family right there. Oxygen is going to be less reactive than fluorine, right? And then as we get further away, carbon is going to be like, I guess I could react, or, I could just kind of chill either way, right? Because it's further away. So either it has a choice. It can either lose 4 electrons or it could gain 4 electrons, but it's got a long way to go. So it's just like, man, that's a lot of work. So, I don't know. I don't want to put a lot of effort into it. So it's not going to be very reactive, not as reactive as other things. Do you guys have charcoal? Charcoal. Okay, so does charcoal just light on fire on its own? You have to put something on it to get it started, right? You have to light it up. You have to get it started. That's a good example. Carbon is just charcoal, right? Where fluorine gas, you put it on anything, it pretty much starts igniting immediately, right? With anything. Because it's like, oh yeah, let's go. Let's get started. Carbon, if you breathe, they're not the same thing. Carbon dioxide is different than just carbon. Yeah. Okay. Okay. So you guys kind of understand that. You understand what is the significance of the families? So if you're in the same family, you're going to kind of behave very similarly, right? So oxygen, we would assume oxygen is going to behave kind of like sulfur, right? Because they're in the same family. Which one is the most expensive element on the periodic table? That is a very good question. I'll actually have to look at the market. Some of the metals are very expensive. Mercury is not the most expensive, no. It would probably be something like platinum, or I'd have to look at the shares of platinum and gold right now. Yeah, or wait, let me take that back. Something like uranium would also probably be pretty expensive as well. What was that? What do you think is my favorite element? I like bling, right? I don't like wearing bling, but I like bling, right? So either it's going to be carbon, because carbon is used to make diamonds, or it's going to be gold, right? Okay. Now back to the lecture here. Oops. Yes. Okay, so we talked about the alkali metals. So this is just an example. So this is just basically showing you what happens when we put lithium in the presence of water. So you get steam and everything like that. You get a little bit of a combustion reaction. If you put sodium in the presence of water, you get a nice little explosion. You go, psh, it shoots up. Okay. Same thing happens with potassium. Okay, in the presence of water. Now that's just water, right? So that gives you an idea of that these metals are very unstable, right? So if they're exposed to air, they have instability associated with it. Air will just cause them to react as well, right? So they have to be packaged specially, right? To sit there and do that. Now, in the case of the halogens are very reactive. So here we have chlorine and phosphorus. Very, very explosive reaction. What was that? No, that is not getting lit. That's just them coming together, right? So that's what I'm telling you, is that these chemicals are so reactive that just exposure to the air can cause reactions to occur. In the case, exposures to just general phosphorus is going to cause this reaction to occur. That's not putting any energy into it. That happens just by them coming into contact. You guys understand? So these are reactive chemicals. These are reactive elements. Because they're so close to being a noble gas, they're very, very volatile. Okay, what was the question? Why do you think it does that? Now think about what we've talked about. So why do you think they're so reactive? Because they're unstable, and also because they're just one away, right? So they're anxious to react, right? So that's the instability has a result for them being one away from being perfect, right? So if you're one away from being perfect, your parents, let's say your parents, I love you if you do all of this, right? Now your parents don't love you now. I'm not saying that they don't, but let's say they don't love you. They never loved you. They are always mean to you and all that. But if you just did this, this, and this, right? Most of you guys would be, okay, I'm going to do this, this, and this, right? And they say, well, you're perfect now. And then you get all the presents and everything like that. You're going to do just about anything to get to perfect, right? Or at least most of us would, right? And so that's the same thing that's happening here. They have to do one thing. They have to gain one electron. Wouldn't you do just about anything to gain one electron? Wouldn't you be anxious to do it? Wouldn't you be volatile? You know, reactive, you go off the handle just to get that one electron, right? So that's why they're reactive, right? Because they're just this close. They really need it. They really, really want to be perfect. They're that close to it. That's why we have reactions, right? Does that make sense? Yes. So yes, because what's happening is they're taking that electron from that other guy, right? Or they're sharing that electron. And so then it allows them afterwards, if you notice, after it happens, they're good. They're like, oh, I'm happy now, right? They're like a noble gas, right? They're not a noble gas, but they're like it, right? They have the stability. They're almost as perfect as a noble gas, okay? Okay, so these are some of the families on the periodic table that you need to be familiar with. Well, familiar with. So I've talked to you guys about the alkaline metals. So those guys are in group 2. They're 2 away, right? 2 electrons away. They need a little bit of help, right? They're not the alkali metals. They're not just going to react instantaneously and start, you know, because they've been exposed to oxygen. It takes a little bit to get them to actually react, okay? So they're not going to be as volatile as the alkali metals are. And I've already talked to you about the halogens. They're 1OA. So then they're going to be very anxious to react. Okay. So this is just giving you an idea of what those metals look like, the alkali and alkaline metals. Take a look at them. You see that luster. That luster is like shininess to it and all of that. These guys particularly, right? You see how they're being handled? This guy has to be drenched in oil to be handled in the atmosphere, or it has to be in an area where there's no atmosphere or anything like that, because it reacts. Moisture causes it to react. Oxygen will cause it to react. So you have to control the environment. So we actually, in 1A, we do an experiment with some of these, the alkali metals. So you guys get an idea of the impact it has. Now, a little piece, one day I was playing with it in class, and I did a demonstration in class. And normally I'm pretty good about weighing it and all of that. And I was anxious, really anxious. I had a much bigger piece than I had planned to have, and I stuck it in water, and it just says, massive explosion. My ears were ringing for days, about 3 days of ringing. It just gives you an idea how volatile it can be. That was just a little chunk, right? Because it can only order so much. I only took a little chunk. So you could imagine if you had a chunk as big as this guy right here, right? That would be huge, a huge type of reaction that occurs. I just put it in water, yes. And it blew up, yes. So where we can put magnesium, we'll be playing with magnesium later on next week. You guys will get to see the type of reactions that magnesium has. It is nothing compared to what you would get with sodium. Sodium alone is very, very reactive. Magnesium isn't so much. They're in two different groups, right? They're in two different families, right? One that's very reactive, the alkalis, and then one that's less reactive, the alkaline, okay? Are you guys clear on that? Okay. So hydrogen is kind of a special case. And the reason why it's above the metals is because it does something that acts kind of like the metals when it's in water, okay? Or when it's in a compound in water, okay? And we'll talk about that. It's the formation of acids. We'll talk about that a little bit later, so. Okay, let's see. So we have metals, we have non-metals, right? So characteristics of metals, right? The metals are going to be, they're going to have luster, they're going to be ductile, they're going to be malleable, they're going to be able to conduct heat. I like this. Ductile, well, malleability is basically that flexibility. You know, you're able to sit there and bend it and all of that stuff. So malleability. Ductility is kind of like that stretching of it, right? So you can actually stretch out metals and make it thin and all of that. So that's the ductility, okay? So your metallic characteristics is going to increase as you go from right to left. And then it's going to decrease as we go from right to left. So let's see, look at the periodic table. So as we go in this direction, we're going to become more metallic. And that kind of makes sense because over here, we have the non-metals, right? And then as we move this way, we start to get metals. So that should make sense. It shouldn't be anything that's surprising, right? And it's also going to go from top to bottom. So francium is going to have the most metallic characteristics of all the metals. So it's going to be really, really, that's the real metal, you know? Okay, we have non-metals. These are our non-metals, right? Here in green. So let's see, non-metals. We have metalloids. Metalloids have both characteristics of metals and non-metals. Let's talk about non-metals to give you some of those characteristics. They're going to be dull, they're going to be brittle, they're going to conduct electricity and heat very, very poorly. So if you're using something for insulation, are you going to use a metal or are you going to use a non-metal? Insulation. So in other words, you don't want heat to be conducted. You don't want heat to be, or electricity to be conducted. Non-metal, okay? So insulation is basically, it's kind of like what we put in the walls, right? So we insulate it to try to keep the cold air in, right? You guys don't want it to be 115 degrees when it's in here, when it's 150 degrees out there, right? So we use insulation to kind of keep the cold air in. So in that case, are we going to use a metal or are we going to use a non-metal? Non-metal, because we know that metal conducts heat. What do we use to cook? Metal, right? And that makes sense. If I want heat to be conducted, I'm going to use a metal. If I don't want it to be conducted, I'm going to use a non-metal.
Okay, I have a question as far as what you just said, Dr.
Yep.
Henry.
Yes.
Okay, so as far as metal and heat, now, are you mean like as far as gas, the form of heat, or would it be the same, like say, like if the stove is electric, and like say if you're baking with a Pyrex, which is glass, but heat is still being conducted.
Conducted. Yeah, but if you think about it, when
So,
you're baking with Pyrex, right? You basically have the top exposed,
yeah,
right? And glass is a composite, so it's a little bit different, but that the fact that you got the upper part exposed, that means that you're able to sit there and do it. If you had a metal pan, it's going to conduct better, right? So typically, if we're going to cook in a glass pan rather than a metal pan, a glass pan is going to cook a lot slower than a metal pan.
yeah.
So depending on what you're doing, it's going to conduct electricity a lot less compared to a metal pan. So we have that aluminum pan, and you want it to cook it fast, you're going to use the aluminum pan because it conducts heat a lot better.
Right.
And so, and either way, it's heat. Heat is conducted better with metal. So whether you're using a gas stove or electric stove, I mean, of course, everybody likes using gas because you feel like you can control it a little bit better, right? Where the electric one is like, oh, is that coil really working? Or, you don't get that evenness as you get with that gas.
Okay.
But that's the question. Any other questions? Great, so we can move on. So this basically just gives you an idea of the physical and the chemical characteristics of metals and non-metals, right? So you guys want to be familiar with this. This here just shows you where the metals and non-metals are located. And this just shows you where how the metallic characteristics increase. Okay, questions, concerns? Okay, so cation, positive charge, anion, negative charge. This basically is just showing you, this here is an example of what we call elements that are ions, monoatomic ions that are isoelectronic with neon. Isoelectronic basically means it has the same number of electrons that neon has. So in other words, these ions became like that noble gas. It reached that point that it wanted to reach, right? So for instance, nitrogen. How many electrons does nitrogen need to be like neon? It needs 3, right? So nitrogen is right here. So that's 1, 2, 3. So it needs 3 electrons to be like neon. So if it gets its 3 electrons, it's going to be isoelectronic to neon. What is going to be the charge on nitrogen? N what? N3 minus. That is correct. Okay, oxygen. How far is oxygen away from being like neon? Okay, so how many electrons will it need to gain to be like neon? So it needs to gain those 2 electrons. Okay, simple. Okay, so these guys, N3O2, these guys are called monoatomic ions. Why do you think they're called monoatomic ions? We'll say it again. Because they have 1. There's 1 nitrogen there, right? So it's monoatomic. And you guys remember, if it was O2, that's diatomic. Okay, so that kind of brings us to, remember what I told you? You have diatomic elements, right? So you guys remember the diatomic elements? Iodine, you mean? Okay. So I heard there's oxygen, there's, okay, so let me make sure I got it right. So you guys said oxygen, nitrogen, iodine, chlorine, fluorine, bromine, and there's one more, and hydrogen. Okay. Okay, so those are our 7 diatomic elements. Now I'm going to introduce you to a diatomic ion. This guy is called the mercury. Oops. This guy's called the mercury 1 ion. Okay, it's called mercury 1 because the charge on it is 1 on each of the mercuries. Yes, ma'am. Yes, you may. Okay, so the mercury 1 ion, do you guys see it up here? Hg, it's 2+, and there's 2 of them. It's a diatomic ion. Okay, it is the only diatomic ion that exists, that I know of at least, or at this point. So you guys want to remember that. So that's going to be added onto a little diatomic, but it's a diatomic ion, the only diatomic ion. And that's mercury 1. What was that? Mercury 1 is the only diatomic ion. Mercury 2 isn't diatomic. I'm going to get to that. It's a good question. This is mercury 2. Okay, mercury 2, again, its charge is 2+, so we call it mercury 2 ion. The mercury 2 ion is not diatomic, right? Meaning that there's not 2 of them that you have to have. Okay, so the distinction between it is that charge. This guy is the mercury 1, right? It's mercury 1 because you have 2 of these guys, so that means that each one of them counts as a 1. You understand? So it has a 1+, where the mercury 2 has a 2+. We also have the mercury 4 ion. Mercury 4 is also not diatomic. Yes, mercury is a metal liquid. When it's an ion, it can be reacting with something to make it solid. Most reactions with a metal and a non-metal are going to be solid at room temperature. Now you can change it to a liquid by heating it up to very, 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 very high temperature. And we'll talk about that here in a minute. Pardon me? To touch mercury? No, they say not to touch mercury because mercury is a poison. So it's going to be a little different. So let me kind of table that for a second, because we'll get to it here in a second. But here, all of your transitional metals and your post-transitional metals, these guys, they're not going to behave like our alkali and alkaline metals, right? So they're not so much looking to try to be like a noble gas. They're like, have you ever met somebody who's just like such a hot mess? They're like just a total mess that you're like, okay, if they just get dressed and comb their hair, they're okay, right? Have you ever met anybody like that? Okay, so The transitional metals are kind of like those people that you're like, you give them the bare minimum. You ate today, you're doing good. You get a star by that, right? So they're those special cases, right? So they're not going to try to be like the noble gases the way that we think of it. They're going to have to do other things, right? And so they're going to be kind of dictated by who they're going to be interacting with. So if they're interacting with somebody who's a lot stabler, you know, they're going to behave that way with them. If they're going to interact with somebody who's less stable, they're going to behave kind of like them. They're going to kind of meet that characteristic of who they're with. And we'll talk about that later, okay? I promise you, you'll get it. It'll all start falling together. Okay. Okay, so I'm going to clear this. So these are all monoatomic ions. In this case, these are all cations that are isoelectronic to neon. These guys here, these were all anions that are isoelectronic to neon. Okay, so I'm going to ask you, what does isoelectronic mean again? Anyone? Kalinga, what do you guys think? Isoelectronic. Fireball, what do you guys think?
Someone in the chat said the same amount of electrons.
The same amount of electrons. That is correct. Good job. That is a good job. Yeah, thank you for sharing that. I didn't look at my chat. So somebody in chat, is it Georgina? Georgina basically said the same amount of electrons. So if I say something is isoelectronic, it basically means it has the same number of electrons of whatever we're talking. If we're talking about neon, it has the same number of electrons as neon. Okay? Okay, so this basically just kind of shows you things that are isoelectronic to each other. So for instance, lithium plus is isoelectronic to helium. Helium and hydrogen minus, H minus, is isoelectronic to helium. All of these guys are isoelectronic to neon. These guys are isoelectronic to argon. Okay, that basically means they have the same number of electrons as that noble gas. Yes, Miss Inez. That is correct. The electron configuration will be exactly the same under those circumstances. But that doesn't mean that they're going to have the same number of protons or the same number of neutrons. So they're still different because the protons and the neutrons are going to be originally what they are. They're not changing. Where the electrons are what's going to be changing. Do you guys get that?
Can you say it again?
I said that they're still going to have the same number of protons that they normally have. So neon is going to have a certain number of protons. How many protons does neon have? Anyone? 10. That's right. And then if we're talking about F minus, it's going to have 9 protons, right? Because it's fluorine. Fluorine always has 9 protons. It's never going to change. Okay? You guys understand that? Okay? So where the electrons are going to be what's going to be changing. And that's going to be like the noble gases, not the protons. Okay. Okay, it says, we're going to skip over this because you guys are already very familiar with writing electron configuration. So, and if you're not, you want to make sure you have it. Okay, so when we talk about an ionic compound is bringing together that metal and that non-metal that's coming together to cancel out the charges. Or it's bringing out ions that are positive and negative to cancel out each other's charges. Okay? So an ionic bond is a bond, or it's really an interaction of opposite parts that are coming together. Okay? So nearly almost all ionic compounds are solid at room temperature and pressure. Okay, now if we put a lot of pressure on them, right, we could sit there and change that. If we put a lot of temperature on it, we could sit there and change that. Okay. So they form, in most cases, what we call a crystalline lattice. Crystalline lattice is basically, they're kind of organized, and I'll kind of show you what that looks like here in a second. So the ionic compound always has to have an electronically neutral charge associated with it. So you're bringing them together so that they cancel out that plus and that minus. Let me give you an example. We have sodium and we have chlorine gas. We know chlorine is diatomic. We know when we put sodium and chlorine together, we get something that we are very familiar with. What's that?
Table salt.
Table salt. And that's called sodium chloride, NaCl. Okay, sodium is going to be giving up an electron. Let me draw this a different way so you guys can see it. I should say different color. So sodium is going to be giving up an electron. And we going to balance this out for us here. Okay. And chlorine is going to want to gain an electron. You okay? Okay, so as I said, sodium is going to be giving up an electron, and chlorine is going to be gaining an electron. Now, you have these two charges, these opposites, right? And they're going to be a proximity of each other. And they're like, oh, baby, just what I'm looking for. And they're going to come together, right? And cancel each other out, balance each other's out, their flaws out. They're going to be perfect together, right? So this guy is a +1, this guy is a -1. So you're going to have a 1-to-1 ratio of each one coming together. That's an ionic compound. The total charge on it now, since you have a plus and a minus coming together, is going to be what? If you have a plus, 1 plus, and 1 minus, that's going to be what? Let's do the math. We have a +1, and we have a -1. What would that equal?
0.
Okay. So when you have that plus charge and that minus charge coming together, it should always equal 0. So we write no charge on it, where the ions, Na plus and Cl minus, right? They have charges associated with them. But when they're together, they are neutrally charged. Are you with me? Okay. Okay, so something else about ionic compounds. They're strong, they're very strong. So salt, salt sticks together. It's pretty strong because of those charges. It doesn't just break apart easily, right? If you put salt under a lot of heat, do you guys ever cook with salt? Okay, put a whole bunch of salt in a pan. Does it melt? No, it doesn't. Okay, but if I put salt in water and I stir it up, it dissolves, right? So water can dissociate those two ions, right? Because it's a home wrecker. It gets in between them. It says, it goes to sodium and says, hey, baby, you don't need fluoride. I got you. I got you. And then sodium turns its back, it goes to chloride. And it says, hey, baby, you don't need sodium. I got you. Right? Gets in between them, and then it's not a replacement. It's not truly a replacement. It's just separating. It causes them to dissociate. You know, it's the home wrecker. So literally, water goes in between. Let me go to a whiteboard so you guys can see this. Literally, water goes in between. Oh, you guys don't see it on your side. Hold on. Hold on. Water has a characteristic, it's called bipolar. Water is considered to be bipolar or polar, right? I shouldn't say bipolar. It's polar, right? So because oxygen, and we'll be talking about this today, oxygen is more electronegative than hydrogen. The electrons are going to be spending more time around the oxygen than the hydrogen. It's going to have what we call a partial negative charge. This guy's going to have what we call a partial positive charge. So because this guy is partially negative and partially positive, the partial positive is going to act or interact with which ion? The partial positive is going to interact with which ion? The chlorine or the sodium ions? It's going to interact with which one? Okay, so the hydrogen, right? So the hydrogen, okay, if you look at it like this, part of water is going to be positive or partially positive, not completely positive, but a little bit of positive. And then the other part of water is going to be partially negative. One side is going to act with sodium and one side is going to interact with chlorine. Which one is going to interact with what? So if oxygen is partially negative, who is he going to interact with? Sodium. So literally what happens is that all of the oxygens will surround sodium to keep it away from chlorine. So the oxygens are going to surround the sodium ion, and then the hydrogens are going to surround the chlorine ion. Okay, you guys see that? So literally, water dissociates the two, right? By interacting with them. Okay, that's why I say water is the home wrecker. So in the case of ionic compounds, water can dissociate them, okay, because of the characteristics of being polar. Okay.
So Professor, this structure that you had just drew right now, is this showing like water? I mean, what happens when salt be dissolved in water? Is
That
this
is
what
correct.
you're okay?
Yep.
Okay.
That is correct. Okay, so okay, so I told you that when we put it at high temperatures, You're not going to get any melting of salt, stuff like that. We have to put it at really, really high temperatures to start getting melting. And the other thing is that if we try to conduct electricity, if we put like a battery between just salt itself, it won't be able to conduct. But if you put salt in water, we're able to conduct electricity because of those ions. So it's really good at conducting electricity if there's salt present. Okay? Are you guys with me so far? Can you repeat that, please? It depends on, yeah, which ion you're talking about, right? So if it's sodium, we know that sodium is going to be a plus. If we know if chlorine, we know that that one's going to be a minus, right? Okay, so this is basically showing you the reaction of sodium chloride. So if we put sodium gas and chloride in together, it's very volatile. It's going to be very, very reactive. And since it's very reactive, you're going to end up with salt. Now, can I ask you something? I want you to think about this thing really hard. Do you guys blow up when you guys eat salt? Does anything like this happen to you when you eat salt? Right? Why do you think you don't blow up? What was that? Anybody want to think? Why aren't you guys blowing up? Well, but doesn't it have chlorine? Doesn't salt have chlorine in it? It has sodium chloride. What was that? Huh. Okay, so let's think about this, right? So if we had sodium and we had chlorine that were coming together in our stomach, it would blow up, right? That would be the explosion that happened in our stomach, right? But the reaction has already happened, right? So that meant that they've already exchanged the electrons. And so we get a nice crystal salt, right? Because they're together, they're stable, they're happy, they're not explosive. They don't cause your stomach to blow up. They cause you to get high blood pressure, but not your stomach blowing up, right? Because they're stable already. They've already did the exchange, right? But if you put sodium in your stomach by itself, whoosh, right? If you put chlorine, they used to use chlorine in the concentration camps to kill the cap. What was that? But that's a different type of chlorine. You do put chlorine in the pool, you use a different type. So it's not chlorine gas, because chlorine gas is actually, well, you use that to also kill the stuff that you put in a pool, but it's a different type of chlorine, okay? So. It's the same thing. Salt, sodium chloride is sodium chloride everywhere. The salt in the ocean is the same. You know, so when somebody says, oh, I use sea salt, right? It's just salt. Guess what? You know, it's just salt. The only thing that's different, you probably collected some other crap in there with it as well too. That's the only distinction, okay? It's still sodium chloride, okay? Okay, so this is just showing you what's happening is an exchange. One is taking the electron, or should I say, one is giving away the electron, the other one is going to be taking. So in the case of sodium, sodium is going to be giving up its electron, and chlorine is going to be taking. Okay, simple, right? It's give and take, right? You know, one is giving, the other one is taking, they work out, and then they come together and form this perfect little lattice. So this basically is showing you a crystalline lattice, right? And so literally what you have actually happening is that you have a plus charge, and then you have a minus charge, and you have a plus charge, and a minus charge, and you have a plus charge, and a minus charge, going in a 3D dimensional structure. So you get this nice little cube, what you see here. And so that's what you see with your salt crystal, right? That's what your salt crystal looks like. Okay, this is just showing you a different perspective of exactly what I just told you about, that alternating, right? Between the chlorine ion and the sodium ion, chlorine ion and the sodium ion, chlorine ion and the sodium ion, okay? So this here is just basically showing you that when we melt salt, when we put it in a high enough temperature and we melt it, it can conduct electricity, right? Or if we put it in solution, it also can conduct electricity. Now, covalent bonds are different, right? Covalent bonds are that sharing. We've talked about that. We know that if we're sharing electrons, who's going to be sharing electrons? Metals, non-metals, post-transitional metals. Who's going to be sharing? Who share? Do metals and non-metals share? Do they form, all of them share? They form covalent bonds? I kind of talked about this, I remember. So if I remember correctly, so if you were a thief, I think I told you this story, if you're a thief and somebody had a badass motorcycle, right? Your neighbor had a badass motorcycle and you saw the same badass motorcycle in San Luis Obispo, slow, right? Same badass motorcycle. Now, and you're a thief. Now, would you steal from your neighbor or would you steal from the guy across the town? Okay, so ionic bond is kind of like that euphemism for stealing, right? Because it's about taking, right? Giving and taking. Ionic bonding. So if I'm going to form an ionic bond, is that going to be between metals, just between metals? Or is it going to be between metals and non-metals? Or is it going to be between? So it's going to be between metals and non-metals, right? So that theft, that taking is always going to be between metals and non-metals. So sharing is going to be between whom? So we have metals and we have non-metals. That's what it's breaking down to. So if you're going to be sharing, who are you going to share with? You're going to share with your neighbor. So it's just going to be metals together, or is it going to be non-metals together, or is it going to be?
Non-metals.
It's going to be non-metals. Non-metals are going to share. So only non-metals are able to form covalent bonds. Okay. So covalent bonds are only formed between non-metals. Okay. Ionic bonds are usually between metals and non-metals. Okay. Now there are going to be some special cases that we're going to talk about, you know, and where you're going to have non-metals that are going to act like they're ionic. Okay. You'll let me get to it? Okay, good. Okay, so when we talk about covalent bonds are going to be happening between non-metals. Okay, you guys are familiar with the non-metals? You're able to identify the non-metals? If you're not, you should be able to look on the screen and look on your periodic table to identify, right? We know if we ever go to P table, we just clicked here and that shows me all my non-metals, right? Or I click up here, non-metals. Okay. Not completely. Atomic number. Yeah, so usually if you memorize stuff, you have to memorize stuff, right? But in most cases today, we don't, or at least I wouldn't require you to, I don't require you to memorize the table. You should be familiar with it. You should know that how many valence electrons does carbon have? It has 4 valence electrons. We also know that carbon has 6 protons. Is that true? No. So you should be familiar with it. And the way you become familiar with it is by playing with it, by working. Okay. Okay, now back, we got 10 minutes. So I need to get through 30 slides in 10 minutes. So, okay. So when we talk about covalent bonds, it's basically sharing electrons between 2 atoms. So we're sharing electrons. So for instance, here we have hydrogen and hydrogen, it comes together to share the 2 electrons so that both of them will reach their octet. We talked about the octet, right? We know that everybody wants to reach their octet, right? And we know that hydrogen is a special case. It wants to be like helium, so it only needs 2 electrons around it to reach its octet, right? So, oops. Now, covalent compounds don't conduct electricity. So water, here we have water, is not able to conduct electricity. We have sugar, this is sugar and water, not able to conduct electricity. This here is salt and water. It's able to conduct electricity because of those ions in solution. Because you have that plus and that minus charge in solution, you're able to get flow of electrons. Because electricity is just the movement of electrons in a metal. And then now you're getting movements of electrons in solution by the plus and minuses being available for it to mess with. Okay, oops. So when we look at it, a covalent bond is really just the overlapping of the 2 atoms electronic cloud. So those electrons are going to be overlapping. So it's really just going to look something like this. Okay, so here, this is one hydrogen atom. This is the other hydrogen atom. When they come together, you have the electron clouds circling around both of them. Okay, that's that overlap. Do you guys get that? Do you see that? Okay, we've talked about Lewis dot structures, right? Or Lewis diagrams. Okay, the concept of using the valence electrons to sit there and determine whether something is going to be able to reach its octet. Yes, no? You guys can do it with your eyes closed now? Better learn. Better learn real quick. Okay, so we know in this case we have fluorine. Fluorine has how many valence electrons? It has 7 valence electrons. So each of the fluorines has 7 valence electrons. We want to get it so that it has 8 electrons around each of the atoms. So we're going to set up so that they're sharing electrons. So if each one gives an electron, so they're sharing 2 electrons between the 2 of them. So that's 2, 4, 6, 8 around this fluorine, 2, 4, 6, 8 around this fluorine. So we just use that line to represent 2 electrons are being shared. You guys get that? Simple. Yes, there are exceptions. We'll get to that, I promise you. Yes. Okay, we'll get to those exceptions. So let's kind of work on getting 8. So if I have nitrogen, I have N2. So can you guys draw the Lewis structure for N2? How many valence electrons does each of the nitrogen have? Okay. Okay, 5 here. So altogether, how many electrons are we going to be working with? So we have a total of 10 electrons that we can work with. Okay, how can I set this up so that I have 8 electrons around each of the nitrogens? So you're saying I do this, I put a double bond between it, so then that's 2, 4, 6. That's 2, 4, 6, 8, 10, 12. That's too many. That don't work, right? You said a single bond. So we're just gonna guess our way to the answer. Like that. You're saying, you said 1, 2 dots here? Okay, so you're saying I'm doing this. 1, 2, 3, 4. No? Oh, so you're saying I'm putting 2 here. Okay. There's 2 here. Okay. Okay, so you're saying this. Okay, so then that's 2, 4, 6, 8, 10, 12. Up. Oops. So I have 10 electrons that I'm working with. I need to figure out a way of making it so it works. Okay, so you're saying double line, N, okay. 1 dot on top, okay. And 2 on the sides, on both sides. Okay, so let's do the count. That's 2, that's 4, that's 6, that's 8, that's 10, so that's electrons, okay? Now, that's around this end, that's 2, 4, 6, 7 electrons. Is that 8? Is that reaching this like 8? It's octet? No. So what do I need to do to make it reach the octet? Anybody else want to take a shot at it?
Would it be a triple bond between them
Ah,
and then
a
2
triple
on the
bond.
side?
Okay,
2
that
valence
sounds good.
electrons?
So if we take this guy and put it in the middle, so now we have okay, so altogether that's 2, 4, 6, 8, 10. That's 2, 4, 6, 8 around this end. That's 2, 4, 6, 8 around this end. That meets our criteria. Okay, so we're gonna stop here. We'll pick it up tomorrow. Don't worry, we'll go to like 5th gear tomorrow.